Okay, so once again, good day everyone. So for today, we're going to have a discussion about a memory allocation. Number one is the basic of dynamic memory allocation. Dynamic memory allocation is the process of allocating memory for a program during runtime. So this allows you to create data structure that are flexible in size and can be modified during program execution. In C and C++, dynamic memory allocation is typically performed using two functions. Number one, malloc or malloc and free. The malloc functions allocates a block of memory of a specified size and return a pointer to the first byte of the block. The free functions deallocates a block memory that was previously allocated with malloc. So I will give you an example of how to dynamically allocate memory for an integer in C++ using malloc. So example, variable declaration, int asterisk ptr semicolon. So ptr is equal to open parenthesis int asterisk close parenthesis malloc open parenthesis size of open parenthesis int close parenthesis semicolon. That is allocate memory for an integer. Then asterisk ptr is equal to 10 semicolon. That is assign a value to the integer. Then free open parenthesis ptr close parenthesis semicolon. That is free the memory. Okay. In that example, no, we declare a pointer ptr of type int asterisk and allocate memory for an integer using malloc and the size of operator. We then assign a value to the integer using the dereference operator asterisk and free the memory using free function. In C++, you can also use the new and delete operators to perform dynamic memory allocation. So the new operator allocates memory for an object of a specified type and returns pointer to the object. No? So the delete operator deallocates memory that was previously allocated with the new function. So an example of how to dynamically allocate memory for an integer in C++ using new. Let's say our data types int space asterisk ptr semicolon. Then ptr is equal to new space int semicolon. That is allocate memory for an integer. Then asterisk ptr is equal to 10 semicolon. That is assign a value to the integer. Then delete space ptr semicolon. That is free the memory. So in that example, no, we declare a pointer ptr of type int and allocate memory for an integer using new. We then assign a value to the integer using the dereference operator asterisk and free the memory using delete. It is important to note that when you allocate memory dynamically, you are responsible for deallocating the memory when it is no longer needed. Failure to deallocate memory can result in memory leaks, no, which can cause your program to run out of memory and crash. It's also important to avoid memory-related errors such as dangling pointers and wild pointers, which can cause undefined behavior and other issues in your code. Okay, so
here in this presentation, we will discuss some of the basics of dynamic memory allocation. So let's get started. First, we will discuss about static memory allocation, then we will move to dynamic memory allocation. Memory allocated during compile time is called static memory. It should be very clear that the memory allocated during compilation time or the time when the programmer is creating the program is called static memory. And the memory allocated is fixed and cannot be increased or decreased during runtime. If you run the program, obviously the memory which has been allocated at compile time is fixed and cannot be increased or decreased. For example, here you can see that we have an array which consists of 5 elements, although you can see over here that the size is fixed. So memory is allocated at compile time and obviously here the size is fixed. The programmer has fixed this size and we cannot increase this size or decrease this size at runtime. It should be very clear. Now there are certain problems which we faced in static memory allocation. If you are allocating memory for an array during compile time, then you have to fix the size at the time of declaration. Obviously, there is least flexibility because you have to fix the size at the time of declaration itself. Size is fixed and user cannot increase or decrease the size of the array at runtime. This size is fixed. User cannot increase or decrease the size of the array or any object at runtime. If the value stored by the user in the array at runtime is less than the size specified, then there will be wastage of memory. Let me tell you that. Here I'm talking about array. It could be any object, right? So if the value stored by the user in the array at runtime is less than the size specified, if the user enter elements less than the size specified, then obviously there will be a wastage of memory. If the value stored by the user in the array at runtime is more than the size specified, if he or she enters more elements in the array, then obviously the program may crash or misbehave. This is also a possibility, right? Now, here comes someone to rescue. The one who can solve the problem is dynamic memory allocation. The process of allocating memory at the time of execution is called dynamic memory allocation. It should be very clear that the process of allocating memory at the time of execution is called dynamic memory allocation. You are allocating memory at runtime. So user has the flexibility. He or she can allocate memory according to his or her needs, right? You might have remembered this diagram from C programming lectures. This is nothing but a memory layout of C program. These are the different memory segments. The one which we will talk about here is the heap memory segment. Heap is the segment of memory where dynamic memory allocation takes place. Unlike stack where memory is allocated or deallocated in a defined order, heap is an area of memory where memory is allocated or deallocated without any order or randomly. In stack, everything is defined in order. You have to enter elements at the top of the stack. You have to delete elements from the top of the stack. Everything is well defined and everything is in the order. So memory is allocated or deallocated in a defined order in case of stack. But in case of heap, there is no restriction as such. Memory is allocated or deallocated without any order or randomly. There are certain built-in functions that can help in allocating or deallocating some memory space at runtime. It is interesting because there are certain built-in functions available that can help us in allocating or deallocating some memory space at runtime in heap. Before revealing those functions, I would like to discuss one very important point. Pointers play a very important role in dynamic memory allocation, and this is one such application of pointers. Allocated memory can only be accessed through pointers. The only possible way which we can access the memory allocated dynamically is through pointers. Now here are certain built-in functions that I was talking about. Malloc, calloc, realloc, and free. These are the built-in functions which are used to allocate or deallocate memory dynamically. We will discuss all these functions in the subsequent lectures. Okay friends, this is it for now.
Okay. So now we may proceed to a dynamic memory allocation using malloc, no? So in C and C++, dynamic memory allocation can be performed using the malloc functions, no? Malloc stands for memory allocation, and it is used to dynamically allocate memory at a runtime. So basic syntax for using malloc is PTR is equal to open parenthesis cast type asterisk close parenthesis space malloc open parenthesis size close parenthesis semicolon. Okay. PTR is a pointer of type cast type and size is the number of type or bytes to allocate. So the malloc functions allocate size bytes of memory and returns a pointer to the first byte of the allocated block. So the pointer is a cast to the type specified by cast type. Example of how to allocate memory for an integer using malloc. So int space asterisk PTR semicolon. PTR is equal to open parenthesis int asterisk close parenthesis space malloc close open parenthesis size of open parenthesis int dalawang close parenthesis semicolon. It is to allocate memory for an integer. If open parenthesis PTR is equal to null close parenthesis begin print open parenthesis double quotation memory allocation failed double quotation close parenthesis semicolon. Exit open parenthesis 1 close parenthesis semicolon then end. So asterisk PTR is equal to 10 semicolon. That is assign a value of the integer. In this example, we declare a pointer PTR of type int asterisk and allocate memory for an integer using malloc and the size of operator. We also check if the memory allocation was successfully by checking if the pointer returned by malloc is null. If the memory allocation fails, we print an error message and exit a program. Okay. Then, once the memory has been allocated, we can assign a value to the integer using the dereference operator asterisk. It is important to note that when you use malloc to allocate memory, you must also free the memory using the free function when it is no longer needed. Example of how to free the memory allocated is in the previous example is the free open parenthesis PTR close semicolon. That is to free the memory. In this example, we use free functions to deallocate the memory that was allocated using malloc. And this is an important step to avoid memory leaks and to ensure that your program does not run out of memory.
Malloc function. So let's get started. What is malloc? Malloc is a built-in function declared in the header file stdlib.h. It is a built-in function declared in this header file stdlib.h. Okay. Malloc is the short name for memory allocation and is used to dynamically allocate a single large block of contiguous memory according to the size specified. So you specify some size in the malloc and it will allocate a single large block of contiguous memory. So syntax of malloc is clear that malloc requires a size and it will return a pointer, basically a void pointer. Malloc function simply allocates a memory block according to the size specified. Here you can see the size needs to be specified and malloc will allocate a memory block according to the size specified. And on success it returns a pointer pointing to the first byte of the allocated memory. Else it returns null. As simple as that. On success it returns a void pointer. If it fails somehow, then it will return null. So the job of malloc is to allocate memory at runtime, and that must be clear to you. Apart from this, you should understand that size t, which I have specified over here, is defined in stdlib.h as unsigned integer. This I have already told you in the C programming lectures, but I am specifying here it once again that size t is nothing but an unsigned integer, the largest unsigned integer possible. Okay. Here, size t size means you should specify the size in an unsigned integer form. Obviously, the size cannot be negative, right? So it should be an unsigned integer. Now, here you can see the pictorial representation of a heap memory. Just an imagination. And here some contiguous block of memory has been allocated by malloc. And malloc will return a pointer which is basically a void pointer. We are assuming that this pointer is PTR. So PTR is the pointer which is pointing to this particular memory. Now, why malloc returns void pointer? Malloc doesn't have an idea of what it is pointing to. Let me tell you that. Malloc simply allocates memory for us. It doesn't have an idea of what it is pointing to. It simply means that it doesn't have an idea about what data will be stored in that memory location. It merely allocates memory requested by the user without knowing the type of the data to be stored inside the memory. So it doesn't know the type of the data at all. That is why it is returning a void pointer. It simply allocates memory for us without even knowing the type of data to be stored inside the memory. How it will know the size beforehand? We just want malloc to allocate some memory for us. After that, it is our responsibility to typecast it to an appropriate type so that we will use it in our program properly. Void pointer is a pointer which can point to any type of data. Malloc returns that void pointer because it doesn't know which type of data will get stored inside that memory. Here you can clearly see that we are asking malloc to allocate 4 bytes of memory. Here if you are specifying 4, it means that we want the malloc to allocate 4 bytes of memory. Now with this, malloc will return a void pointer if it is a success. In that case, we need to typecast it to an integer type of pointer because we want to store an integer within that memory location. Malloc simply allocates 4 bytes of memory and it will return a void pointer. We will typecast it to an appropriate type and then after that we will store that address within some pointer of our choice. As simple as that. Here we are typecasting the pointer. We want to store an integer. That's why we have typecasted it to an integer pointer. After that we will store the address returned by the malloc in this PTR pointer. It could be any name, doesn't matter. But here my choice is PTR. Malloc allocates 4 bytes of memory in the heap and the address of the first byte is stored in the pointer PTR. As simple as that. So the address of the first byte is returned by malloc, and that will get stored within this PTR pointer. From there, we can access the rest of the bytes. Here is a simple example program I want to show in order to understand the concept of malloc in a proper way. Here you can see with the printf function I'm asking the user to enter the number of integers. We have declared two variables over here, one is I and one is n. N is the place where we will store the number entered by the user. Here we are asking the user to enter the number of integers. We'll store that value within this n variable using this scanf function. After that we have a malloc function. What we are doing here is we want the malloc to allocate the size equivalent to the size of n integers. That's why I have put here n into size of integer. Why size of int? We don't know what is the size of integer in our computer. That's why we are using the size of operator. With this, we will multiply this with n. This will give us the size of n integers. We are asking the malloc to allocate memory for n number of integers. After that, obviously malloc will return a void pointer, and we are typecasting it to an integer pointer, and we are storing the address within this PTR pointer. Typecasting is important. You should do the typecasting. It's a good practice. Okay. If pointer contains null, then it means that memory is not available. So we'll simply exit out of the program with the exit failure status, right? If this is not the case, then we can easily run the for loop from 0 to n-1, and we will ask the user to enter an integer one by one. So here in this case, obviously this loop runs from 0 to n-1. We are asking the user to enter an integer every time. Now here you can clearly see within this scanf function, there is one thing written over here, ptr plus I. What does it really mean? We know that ptr contains the address of the first byte of the memory. Let's say that address is 1000. Here I is equals to 0 initially, so this is 1000 plus 0, which is 1000. So within that address, our first integer will get stored. Then after that, when I becomes 1, here this becomes 1000 plus 1, which has internally been interpreted as 1000 plus 1 into 4. If I'm assuming that size of integer is 4 bytes, then obviously this will be 1000 plus 1 into 4. This we have already learned in our C programming lectures. If you have any problem in understanding this concept, it is better to see C programming lectures created by us. Here you can see this is ptr plus I. If I is equals to 1, then this will be 1000 plus 1, which is interpreted as 1000 plus 1 into 4, which is equal to 1004. So the next integer will get stored in 1004 location, and this will continue in this way. So the addresses are like 1000, 1004, 1008 and so on. And let me tell you why we are not using ampersand over here. Here we need ampersand because n is representing the value. We need the address. Scanf requires the address. That is why we have to put ampersand over here. But ptr is already giving us the address. When we simply write ptr, which is a pointer, pointer contains the address and not the value. That's why there is no requirement of putting an ampersand in front of it. So this concept needs to be clear. After that, we have a for loop again, where we are simply doing one thing. We simply want to print all the integers on the screen. Obviously, we are using ptr plus I, but here in this case, we are dereferencing it. Because this represents an address, we need to dereference it. If I is equals to 0, this will be 1000 because we are assuming the first address is 1000. So we are dereferencing it, then we'll get the first integer. With this, when I equals to 1, then this will be 1000 plus 1, which is interpreted as 1000 plus 1 into 4. If size of integer is 4, then this will give us 1004. We are dereferencing it, so this will give us the second integer. In this way, everything works. So basically, this is a simple program which is asking user to enter n integers, and then we are simply displaying those integers on screen. Let's execute the code in our favorite IDE. Now you can clearly see the program is available in front of you. Let's execute this code. It is asking us to enter the number of integers. Let's say we want 3 integers to be entered. Let's enter one integer. Let's say it is 43. Let's enter the second integer. It's 56. Let's say it is 78. Now it is displaying all the integers on the screen. That's what we want, right? First, we are asking the user to enter the number of integers. Then after that, the user is entering the integers. And then we are simply displaying them on the screen. 43, 56, 78 will get printed on the screen. Okay friends, this is it for now. Thank you for watching this presentation.
Okay, so right after that, of course, how about the dynamic memory allocation using calloc? A while ago, we use malloc. So how about the dynamic memory allocation using calloc? Okay, collocation, no? So in C and C++, dynamic memory allocation can be performed using the calloc function. So calloc stands for contiguous allocation, and it is used to allocate multiple blocks of memory of the same size and runtime. So the basic syntax of for using calloc is PTR is equal to open parenthesis cast type asterisk semicolon, close parenthesis rather, calloc open parenthesis n comma size close parenthesis semicolon. So PTR is pointer of type cast type n, in is the number of elements to allocate, and size is the size of each element. So the calloc function allocates n blocks of memory of size no, and returns a pointer to the first byte of the allocated block. So the pointer is cast to the type specified by cast type. So example of how to allocate memory for an array integers using calloc functions: int space asterisk ptr semicolon. PTR is equal to open parenthesis int asterisk semicolon. Open parenthesis PTR is equal to open parenthesis int asterisk close parenthesis space calloc. Let's say close parenthesis 5 comma size of, then open parenthesis int close parenthesis semicolon. That is to allocate the memory for an array of 5 integers. So if open parenthesis PTR is equal to null, close parenthesis, begin. Print f of close parenthesis double quotation memory allocation failed double quotation close parenthesis semicolon, exit open parenthesis 1 close parenthesis semicolon. And in this example, no, we declare a pointer PTR of type int asterisk and allocate memory for an array of 5 integers using calloc and the size of operator. We also check if the memory allocation was successfully by checking if the pointer returned by calloc is null. So, if the memory allocation fails, we print an error message and exit the program. So once the memory has been allocated, we can access the elements of the array using the array indexing notation. It is important to note that when you use calloc functions to allocate memory, you must also free the memory using free functions when it is no longer needed. Example of how to free the memory allocated in the previous example, right after the program, you just simply add free, open parenthesis PTR, close parenthesis semicolon. That is to free the memory. So in this example, we use the free functions to deallocate the memory that was allocated using calloc. And this is an important step to avoid memory leaks and to ensure that your program does not run out of memory. Okay? So example of a calloc applications in programming.
In this presentation, we will try to understand how memory is allocated dynamically using calloc function. So let's get started. What is calloc, by the way? Calloc function is used to dynamically allocate multiple blocks of memory. So it is a built-in function that too declared in stdlib.h like malloc function, and this function is used to dynamically allocate multiple blocks of memory. It is different from malloc in two ways, let me tell you. The first is that calloc needs 2 arguments instead of just 1. Here is the syntax of calloc. Calloc needs 2 arguments. The first argument represents the number of blocks and second argument represents the size of each block. As simple as that. So calloc needs 2 arguments instead of just 1. In case of malloc, obviously 1 argument is required. Here in this case, 2 arguments are required. Here is a simple example of calloc allocating memory. Here you can clearly see calloc is allocating 10 blocks of memory and each block size is equal to the size of integer. An equivalent malloc call is like this, where you need to do this calculation. 10 is multiplied by size of integer. It means that 10 blocks of memory has been allocated where each block size is equal to the size of integer. Both are doing the same job, but here you can see the syntax is different. Now let's discuss difference number 2. Memory allocated by calloc is initialized to 0. It is not the case with malloc, let me tell you. Memory allocated by malloc is initialized with some garbage value, while in the case of calloc, it is initialized to 0. This is very important point, let me tell you. When memory is allocated by calloc, automatically all the blocks have been initialized to 0. Please note that malloc and calloc both returns null when sufficient memory is not available in the heap. Calloc stands for clear allocation and malloc stands for memory allocation. Here M stands for memory and C stands for clear. Okay friends, this is it for now. Thank you for watching this presentation.
Okay. Now, how about the dynamic memory using realloc functions, no? So we were done already with malloc, calloc. So this time, dynamic memory allocation using realloc. Okay. In C and C++, the realloc function is used to dynamically resize a block of memory that was previously allocated using malloc, calloc, or realloc itself. The basic syntax of using realloc is PTR is equal to realloc, open parenthesis, PTR, comma, new size, close parenthesis, semicolon. PTR is a pointer to the block of memory that we want to resize, and new size is the new size of the block. The realloc functions resizes the block of memory pointed to by PTR to new size bytes and returns a pointer to the first byte of the resized block. So if the realloc function is unable to resize the block of memory, it returns null. Example of how to resize the block of memory using realloc. In space asterisk PTR semicolon. So asterisk PTR, of course, asterisk is a pointer, no? As what we discussed earlier. So PTR is equal to open parenthesis int asterisk close parenthesis space malloc open parenthesis 5 asterisk size of open parenthesis int dalawang close parenthesis semicolon. That is to allocate memory for an array of 5 integers. If open parenthesis PTR is equal to null close parenthesis begin, printf open parenthesis double quotation memory allocation failed double quotation close parenthesis semicolon. Exit open parenthesis 1 close parenthesis semicolon and end. Then PTR is equal to open parenthesis int asterisk a close parenthesis space realloc rather double open parenthesis PTR comma 10 multiplied by size of open parenthesis int dalawang close parenthesis semicolon. That is to resize naman the block of memory to 10 integers. If open parenthesis PTR is equal to null close parenthesis then begin printf open parenthesis double quotation memory array allocation failed double quotation close parenthesis semicolon. Then exit open parenthesis 1 close parenthesis semicolon and end. In that example, no, we allocate memory for an array of 5 integers using malloc and the size of operators. We also check if the memory allocation was successfully by checking if the pointer returned by malloc is null. If the memory allocation fails, we print an error message and exit the program. So, we then use realloc to resize the block of memory to 10 integers and check if the reallocation was successfully by checking if the pointer returned by realloc is null. If the memory reallocation fails, we print an error message and exit the program. So once the memory has been resized, we can access the elements of the array using the array indexing notation. It is important to note that when you are realloc to resize a block memory, the contents of our original block may be moved to a new location in memory. Therefore, any pointers that refer to the original block of memory may become invalid after the resize operation. It is also important to note that when you use realloc to allocate memory for the first time, it behaves like malloc. Okay? So another example.
In this presentation, we will try to understand how to dynamically allocate memory using realloc function. So let's get started. What is realloc, by the way? Realloc function is used to change the size of the memory block without losing the old data. It's a special type of function, obviously, which is used to change the size of the memory block without losing the old data. It is a built-in function, again declared in stdlib.h, and as the name itself suggests that realloc, which means reallocation. Obviously, it means that it is changing the size of the memory block. Now the syntax is quite clear. Here you can clearly see that obviously it will return a void pointer. Apart from this, it requires 2 arguments. The first argument is the pointer to the previously allocated memory. It needs the pointer to the previously allocated memory, and obviously it also needs the new size. Now on failure, realloc returns null. Similar to the other functions, realloc also returns null. Let's consider one example here. Let's say we have a malloc function which allocates memory for one integer. Okay, here you can see size of integer has been specified here, which means it will allocate, let's say 4 bytes, because we are assuming that size of integer is 4 bytes. So malloc will allocate 4 bytes in heap. Let's say somewhere in my code, I reallocate the memory. In this case, obviously the pointer to the previously allocated memory is required. and second argument is the new size. Here in this case, I want one more integer to be allocated. That is why I have to consider the previously allocated memory as well. Here in this case, I should specify 2 into size of integers. So the total memory which is available with me is of 8 bytes. So previously we have 4 bytes, now we have 8 bytes. This particular function will return an address and that will get stored within this PTR pointer. This is quite an interesting function, isn't that so? Let's consider some points related to it. This will allocate memory space of 2 into size of integer, which is equivalent to 8 bytes because we are assuming size of integer is 4 bytes, right? Also, this function moves the contents of the old block to a new block, and the data of the old block is not lost, let me tell you. This is interesting because this function is actually allocating new memory, but it is also taking care that old data should not be lost. So this function moves the contents of the old block to a new block, and the data of the old block is not lost. We may lose the data when the new size is smaller than the old size. Okay, so here you can see the new size is greater than the old size. So the data will not be lost, but when the new size is smaller than the old size, then the data may get lost. Apart from this, newly allocated bytes are uninitialized. The bytes which are allocated newly by this realloc function will not get initialized. Okay, we should initialize them. That should be very clear. Now, let's consider one programming example in order to cement this concept. Here you can see that we have a malloc function. Obviously, this malloc function is allocating 8 bytes of memory. You can see over here, this is 2 into size of integer. Again, the assumption is size of integer is 4 bytes, so total bytes allocated by this malloc is 8 bytes on the heap memory. This malloc function will also return the address of the first byte of the memory, which will get stored within this PTR pointer. We should check this also. If PTR is equal to null, then memory is not available, and we should exit from the program with exit failure status. Otherwise, we can continue. Here in this case, we are asking the user to enter the two numbers. Now with the help of realloc function, what we are trying to do here is, we are trying to allocate memory for 2 more integers. Here you can see the size specified over here is 4 into size of integer. Here we should note this very carefully that we should keep the count of the previously allocated memory as well. Okay, that is why it has to be 4 into size of integer. We want 2 more integers. Previously we have the memory for 2 integers. Now we want 2 more integers. That's why I have to specify 4 into size of integer. Obviously, here in this case, PTR has to be passed, which means the pointer to the previously allocated memory. Realloc function will allocate memory for 2 more integers. If it is the case that PTR is null, then again, we should print this out on the screen that memory is not available. Else, we will ask the user to enter 2 more integers and we will store those integers within this newly allocated memory. You can see the for loop starts from I equal to 2, let me tell you, instead of starting it from 0. After this, we have the step that is printing the values on the screen. As simple as that. We will print all the values entered by the user, and that's all. Let's execute this program. So let's enter the 2 numbers. Let's enter 2 more integers. Let's say this is 79 and this is 90. You can clearly see over here that all the 4 integers get printed on the screen. This is how realloc function works. Okay friends, this is it for now. Thank you for watching this presentation.
Okay, so the last one, of course, is the releasing the dynamically allocated memory using free. Okay, so this will be the last one for the dynamically allocated memory. No, in C and C++, the free function is used to release dynamically allocated memory that is no longer needed by the program. So when when you allocate memory dynamically using functions such as malloc, calloc, and realloc, it is your responsibility, of course, to release the memory when it is no longer needed in order to avoid memory leaks. No, a basic syntax for using free is the free open parenthesis PTR close parenthesis semicolon. So PTR is a pointer to the block of memory that we want to release. So the free function releases the block of memory pointer to by PTR, making it available for reuse by the program. Example of how to release dynamically allocated memory using free: int asterisk space, of course, space asterisk PTR semicolon. PTR is equal to open parenthesis int asterisk close parenthesis space malloc open parenthesis 5 do asterisk size of open parenthesis int dalawang close parenthesis semicolon, that is allocate memory for an array of 5 integers. if open parenthesis PTR is equal to null close parenthesis begin, print open parenthesis double quotation memory allocation failed double quotation close parenthesis semicolon. exit, open parenthesis, 1, close parenthesis, semicolon. And to use the memory here, no, you just simply type or add free, open parenthesis, PTR, close parenthesis, semicolon to release the memory. So in that example, we allocate memory pan an array of 5 integers using malloc and the size of operator. We also check if the memory allocation was successfully by checking if the pointer returned by malloc is null. If the memory allocation fails, we print an error message and exit the program. So when we then use the memory as needed and release it using free when we are done with it, it is important to note that once you have released a block of memory using free, you should not attempt to access the content of that block. So doing so can result in undefined behavior, which can lead to crashes or other errors in your program. It's also important to note that you should that you should only pass a pointer to free that was returned by one of the memory allocation functions. So passing any other pointers to free functions can result undefined behavior. So again, to summarize all the discussions of based on the given dynamically allocated operations, okay. Dynamically allocated operations or dynamically allocated memory again refers to the memory that is allocated at runtime as opposed to static memory which is allocated at compile time. Some key points to keep in mind, okay? Dynamic memory allocation is performed using functions like malloc, calloc, realloc, and free in C and C++. Dynamic memory allocations allows program to allocate memory based on runtime conditions such as user input or data processing requirements. Dynamic memory allocation allows programs to allocate in the allocate memory as needed, making more efficient use of memory resources. Number 4, memory allocated dynamically must be released using the free functions when it is no longer needed to avoid memory leaks. Number 5, dynamic memory allocation can lead to errors like memory leaks, buffer overflows, and null pointers dereferences if not used carefully. Number 6, dynamic memory allocation is often used in data structures like linked lists, trees, and graphs, as well as operating system and even the embedded system programming. And last, of course, efficient use of dynamic memory allocation requires a deep understanding of memory management principles and best practices and careful testing and debugging to ensure correctness and stability of the program. So I think that's it for this